So in this video we will be discussing how to solve Laplace's equation in problems with spherical symmetry. The first step is to write Laplace's equation in spherical coordinates. The Laplacian can either be looked up or you can work it out by doing the scale factors first. Now once you have the equation of this form, you have to use the separation of variables concept. So let's try writing capital phi, which is a function of r, theta and phi, as a function of r alone, theta and a function of phi. So it's a product of three functions. If there are solutions that are more general than this, then this method will not yield it. But one of the great things about Laplace's equation is the uniqueness aspect of Laplace's solution. If you find one solution that satisfies it, it's the only solution. Now, for the sake of making this easier, let's write r of r as another function u of r divided by r, p of theta times q of phi. Then if you put this inside, I'll be skipping a few steps and divide all the sides by the product PQ and R. You're going to end up getting 0 equals r squared sine squared theta, where I'm writing s for sine, u double prime. Now the primes here denote the variable with respect to which I'm differentiating. So for example, u would be the variable r, and p would be the variable theta, and so on. So I end up getting this equation, and the details of this can be found in my notes, but I just want to go through the main steps here. Now if you notice, this has got both r and theta. However, this has got only phi. So we can immediately separate the azimuthal part, as it's called. This tells us that q double prime must be equal to some constant times q, because if this is a function only of phi and that's a function of both r and theta, the only possible way these two can add up to be 0 is this is equal to a constant and that's equal to the opposite constant minus c. So we can write this using the Euler ansatz. You get the solution of this equals e to the lambda phi. Let's just choose this to be the solution and let's substitute and see what we get. You end up getting lambda squared equals c, or lambda equals plus or minus root c. But you can't seem to go beyond this, so q just gives me e to the plus or minus root c times phi. But there's one important thing about the function q. It should return to itself after it goes around. So that's called the single valuedness boundary condition. So the single valuedness boundary condition tells us that q of phi plus 2 pi must equal to q at coordinate phi. And this automatically puts a restriction on what possible values of c I can have. If I do this, I get e to the plus or minus root c times 2 pi equal to 1. And that's only possible thanks to Euler's formula if root c equals to Im for all integer values of m. So we can get the azimuthal part. It's indexed by this quantum number m. It's discrete rotations, e to the Im phi, with m equals 0, plus or minus 1, plus or minus 2. Because of its frequent applications in hydrogen atom theory, this is called the azimuthal quantum number. That is, the integer m is called that. Now once we have done that, so remember now the c is equal to, if I square c, I'm going to get negative m squared, which means that this thing is equal to positive m squared. If this is equal to positive m squared, this quantity minus m squared must be equal to 0, so that's what I'm going to write. R squared sine squared theta u double prime over u plus sine theta over p sine theta p prime prime minus m squared equal to 0. Now, I would like to separate this further. That's only possible if you make sine theta somehow not appear here. So what I'll do is I'll divide both sides by sine squared theta. If I did that, the first term is now only a function of r, and that's amenable to further investigation. So sine theta p prime prime divided by p sine theta, because when I divide by sine squared theta, one of the factors of sine theta cancel out, giving me just one factor of sine theta in the denominator. And then I get minus m squared over sine squared theta equal to 0. And now we have achieved the intended separation, because that's a function of r alone, and that's a function of theta alone. So it's a step-by-step procedure. Now this u problem can actually be addressed in a rather nice fashion by using a different kind of ansatz. So again, keeping in mind its application mainly to hydrogen atom theory and atomic and molecular chemistry, I will not be shying away from introducing notation that's consistent with those subjects. So r squared u double prime over u, and that constant is called L times L plus 1, because these are the principal angular momentum quantum numbers. Right now L could be a complex number, but we'll fix what L can be later. And then the other thing will be the minus of that. So s theta sine theta p prime prime over p sine theta minus m squared over sine squared theta is equal to negative L times L plus 1. Now this is not very difficult to solve. You can use what's called the Euler-Cauchy ansatz. And the Euler-Cauchy ansatz says that u must be equal to r to the power lambda. If you work this out, you'll end up getting u is a linear combination of r to the L plus 1 and r to the minus L. Depending on what your asymptotics are going to be, you will choose one or the other. If you want your polynomials at infinity, you will choose this. I said polynomials because this is going to give us the Legendre polynomials very soon. So this equation can be rewritten, and you end up getting an equation of this type: 1 minus u squared p prime prime plus L times L plus 1 minus m squared over 1 minus u squared p equals 0, where u equals cosine theta. So these are precisely the associated Legendre polynomials that we have talked about earlier. So these are the PLMs as a function of cosine theta. So if m equals 0, now this is a very special case. It's not always the case that m is equal to 0, but if it is, then the system is said to possess what's called azimuthal symmetry. So that's a very special case that we'll talk about here for the sake of simplicity. This means that the problem looks something like a spherical object mounted on a long shaft. For example, think about a Van de Graaff generator's sphere on the top. As you go around the Van de Graaff generator, nothing changes. So that system has got azimuthal symmetry. So once you have azimuthal symmetry, you can take m to be equal to 0, and then we are back to our regular Legendre polynomials. So I get the equation 1 minus u squared p prime prime plus L times L plus 1 p equal to 0. And that's actually the Sturm-Liouville form of the Legendre equation. So that's amazing. All the hard work we did studying the Legendre polynomials is paying off in solving real life problems involving spherical symmetry. And so the full solution of problem, if you will, can be written now. Capital phi as a function of r theta phi is going to be the sum from L equal to 0 to infinity, because you have to sum over all of them using the Fourier Legendre theorem. M equals minus L to L e to the I m phi. M only goes from minus L to L. And then I have ALM r to the power L, because this coefficient AL is a function both of L and M, plus another BLM r to the power negative L plus 1 PLM cosine theta. And if M is equal to 0, you just remove this index M here, remove that index M here, remove that M there, and remove the summation, and just keep that one term. So let us actually work out a simple example of trying out how this works in a specific instance. So I have a potential given to us, and let's say the potential is on a Van de Graaff generator. It's a function only of the longitude. Did I say that right? It's a function only of the longitude, because latitude would be this. So cosine squared theta. Now what we want to do is find the potential everywhere. Now immediately you realize that the only value of theta you can have is the only value of the Legendre polynomial you can have is P2, because P2 has got, so let's just at least try to match this with a Legendre polynomial. That's probably the easiest way to do this. You can of course use orthogonal relations and so forth, but it's easier to simply write cosine squared theta. And so what I'll do is this. Cosine squared theta will be the linear combination of A times P2 plus B times P1, P naught. It's not going to have any P1 terms because P1 has got cosine theta. So let's try to solve this. A times P2 would be, P2 is 1/2 3 cosine squared theta minus 1 plus B, P naught is just 1. So I'm basically going to get A over 2 equals B, because the constant terms are not there. And then 3/2 A will just be equal to 1. So this tells me that A is equal to 2/3 and B is equal to 1/3. So I've essentially solved the problem, because I've found the Legendre polynomials that I need to get. So I can write the coefficients A naught, because A naught comes with P naught. So it's just 1/3 V naught over 3 because of the V naught there. And then I have no A1, and then I have A2, which is 2 over 3. But be careful, because of the dimensions, you have to scale it properly. So it's V naught over A squared, because A naught goes with r to the power 0 and A2 goes with r to the power L. In this case it's going to be r squared, so to make the dimensions consistent you have to divide by A squared. You can also do this the hard way, and I've shown it to you in the notes how to do it the hard way, but and that's it, there are no further terms. So the potential for r less than A is going to be v naught over 3 1 plus 2 times r over a squared, and that's it. There are no other terms because the boundary matching allows us only to have these two terms. And then the for r bigger than a, you just have to pick this solution instead. So I get v naught over 3. So this will bring the r factor to the denominator. So that's going to be a over r plus 2 times a over r cubed. So we have found the potential everywhere for this particular Van de Graaff generator.